Hey everybody. Today we're going to answer the question, what do we mean when we use the word probability? Spoiler alert, in the mathematical context, when we're talking about probability, we're talking about a function. In order to get to that, we're going to need a couple of preliminary pieces of terminology. First of all, the sample space of a probability experiment, just sort of a random trial, is the set of all possible outcomes. That could be finite, doesn't have to be though. An event is a subset of the sample space. So an example to try and make that a little bit more solid. We're going to flip two coins and just record the results. So there's four possible outcomes. The sample space consists of the set heads, 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 tails, etc. The event both flips are the same has two outcomes in it, heads, heads, and tails, tails. So intuitively, an event is just something that can happen in a probability experiment, but typically can happen in more than one way. And in that sense, the event E that we have on this slide is completely typical. An event that consists of just a single outcome is called a simple event. The word probability refers to any set function that assigns a real number to every event in the sample space. So remember, an event is a subset of the sample space, which itself is the set of all possible outcomes. This probability function P has to satisfy three properties. First of all, P of S is 1. Basically, the probability that something happens is 1. Secondly, for any event in the sample space, the probability of the event is at least 0, so probabilities are never negative. Finally, if you have two events that don't overlap, they're disjoint, they don't have any outcomes in common, then the probability of one or the other is the sum of the individual probabilities. And that's a property that extends to arbitrarily many pairwise disjoint sets. So if we have E1, E2, and E3, maybe even also E4, same thing. By this definition, more than one probability function is possible for any random experiment. When S is finite and every outcome is equally likely, though, there's a very natural way to do the probability assignments. And it's basically just counting up the number of outcomes in the event, dividing by the total number of outcomes in the sample space. And that ratio is going to satisfy all those probability axioms. This is known as classical probability. For instance, the probability of getting a sum of 3 when you roll two fair dice is 2 in 36, because there are 36 possible outcomes, 6 times 6, and there are two ways that this event can occur. You roll a 1 and then a 2, or a 2 and then a 1. A slightly more involved example is when you flip a coin 3 times and look at the probability that you get exactly 2 heads. The sample space consists of exactly 8 possible outcomes, things like heads, 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 and heads, heads, tails. And the event has 3 possible outcomes. Basically, if you're getting 2 heads, you need to have 1 tail. It can happen on the first, second, or third of the flips. So the probability of getting exactly 2 heads is 3/8. Now, probability assignments don't have to be done that way, and they often can't be. For instance, it's very natural to talk about the probability that a basketball player makes a free throw, saying things like 79% chance that they make their shot. But there's no way to view such a probability in terms of classical probability, like the number of outcomes in the event divided by the number of outcomes in a sample space. Typically what we're doing there is we're looking at the number of times the person has shot, the number of shots that they've actually made, and taking that ratio, going through a process that we call empirical probability. One final example that's a little bit different from either of those other two. We have the unit disk, basically all the points within 1 unit of the origin, and we're going to pick a point at random. For any region E inside of that set, we're going to define the probability that the point lies in the subset E to be the area of E divided by the area of S. And since that unit disk has an area of 1, this probability turns out to be the area of E divided by pi. And you can check, and in fact I recommend that you do check, that all of the axioms of a probability function hold here.